Peace be upon you and God's mercy and blessings. God willing, we will talk about protection system requirements in electrical stations. The first thing we need to ask is, what are the objectives of the protection system? The objectives of the protection system are to maintain power system stability for system quality. This is achieved by the protection system isolating only the components that have faults, allowing the rest of the system to continue running healthily. For the protection system to perform this function correctly, there are certain requirements that must be met in the protection system. Protection system needs reliability, dependability, security, and performance, selectivity, discrimination. They consist of dependability and security. As for the performance requirements, they include selectivity, also known as discrimination, speed, and sensitivity. Alright, let's move on to the first thing we have, which is the reliability requirements. The first aspect of the reliability requirements is dependability. This means that there is no possibility for the protection system to operate if there is a leak in the system. In other words, the protection system must operate in the event of a fault. And to achieve this, I must have a proper system design and a second line of protection, which we refer to as the backup system. This is to ensure that fault clearance occurs even if the main protection system fails to isolate the fault. The second thing is security or safety, which means that there should be no possibility for the protection system to operate in the absence of a fault, or if the fault was present that it is supposed to protect against, because in this case, I would have something called a malfunction. The second thing is the performance requirements. The first thing in the performance requirements is selectivity or discrimination, which means that the protection system can identify the location of the fault in the system and give a trip command or circuit breaker separation order. Only the responsible one, or the one that, if tripped, will isolate only the fault location while the rest continues to operate normally. And as we can see here in this area, we have a set of logical zones. And if a fault occurs in one of them, there is a set of related logical zones that use the trip command from the logical zones and isolate only the logical zones within their area. Secondly, there is the speed, which refers to the speed of fault isolation, or more precisely, we can say that in the event of a zone occurrence, the logical zones must be isolated at the specified time according to the protection function setting. The third aspect is sensitivity, which means that the protection system responds to the slightest change in the values of currents, voltages, angles, and frequency. If these values exceed the predefined settings according to the activation of protection functions, the protection system should be able to read and analyze the different values to determine whether there is a fault or not. Alright, we need to understand something very important. What is the difference between resolution, sensitivity, and accuracy? Resolution is the smallest portion of the signal that can be observed, meaning how many digits you can read. The more digits you can read, the higher your resolution. Sensitivity is the smallest change in the signal that can be detected, meaning if you can read changes in the distant digits, like this digit for example, it means your sensitivity is high. As for the accuracy, it is the closeness of agreement between the result of measurement and its true value, meaning the closeness of the value you are reading to the true value, exactly like the idea of the error percentage. Therefore, the lower the error percentage, the higher the accuracy. Very nice. Now we want to see together an example of the protection system selectivity. We have a single line diagram for a single bus single breaker with a bus sectionizer. Skin consists of 3 incomers connected to 3 buses and 2 bus sections. Breaker and bus sectionizer skin consisting of 3 incomers connected to 3 buses, and there are 2 bus sectionizers. Let's assume all the breakers were closed. Now if a fault occurs on one of the feeders or circuits on bus A, the 3 transformers will start to supply this fault. The protection responsible for this feeder will begin to detect the fault, and based on the protection, it will send a trip command to the feeder circuit breaker. The feeder circuit breaker will open to isolate this fault, and at that point the rest of the system will continue to operate normally with the transformers supplying all the other loads. Alright? Now suppose the protection for this feeder didn't detect the fault, or its sensitivity wasn't enough to detect this fault. Or it detected the fault, but after sending the trip signal, the circuit breaker didn't respond. In this case, there is backup protection on the incomers within the backup protection of transformers T1 and T2. After the protection of T1, the backup protection of the incomers will send a trip on key command to open the bus section circuit breakers. Suppose that after opening the bus section circuit breakers, the fault still exists. We will notice that after opening the bus section circuit breakers, the incomers GT2 and GT3 do not detect any issue. But it is the incomer GT1 that does not detect the fault. Therefore, after applying T2, the relay will issue a command from applying T3 to open the GT1 circuit breaker, thus isolating the fault by isolating the entire bus bar A. However, bus bar C and bus bar B will continue to operate normally, and the attempts to balance their loads will be different. With this, folks, we have completed the application.